In this video, we're going to go over section 10.1 from our textbook, which is on some trig identities. And in fact, chapter 10 is mostly going to be on different trig identities and functions. But for now, we'll start with these here. First, we're looking at the reciprocal identities, which we've seen in the last several videos. We know that cotangent is going to be the reciprocal of tangent. Secant is going to be the reciprocal of cosine, and cosecant is going to be the reciprocal of sine. We should also be comfortable with the quotient identities here, the fact that tangent is going to be sine over cosine, and since cotangent is the reciprocal of that guy, cotangent is going to be cosine over sine. Additionally, we have our Pythagorean identities. We've at least seen this one before, sine squared theta plus cosine squared theta is equal to 1, and then we also have these two identities as well. Now, it'll be important to also recognize alternative forms of these guys. For example here, if we wanted to get cosine squared theta alone, we would subtract sine squared theta on both sides, and we'd get cosine squared theta is equal to 1 minus sine squared theta. And then we can manipulate these guys as well to get alternate forms. Now, something new in terms of trig functions are even and odd identities here. So we should be familiar with what an even and odd function is. An even function has this property here. This means that the value of our function f at a negative input is going to be the same as the value of the function at a positive input. Now, on the other hand, an odd function has this property here. Now, this means that the value of our function f at a negative input is going to be equal to the opposite or the negative of the value of our function at a positive input x. Now, with this, we can see that our trig functions are also going to be even or odd functions. We see that sine here is going to be an odd function, cosine here is going to be an even function, and tangent here is going to be an odd function. And similarly, we have the reciprocals here are going to be odd, even, and odd here. Now let's look at an example. We want to find the correct expression that completes the identity here. So we have 1 minus cotangent squared x is equal to something. Now what we'll do here is we'll use one of our Pythagorean identities. It says that sine squared x plus cosine squared x is going to be equal to 1. So with this, what we can do is we can rewrite this 1 in terms of sines and cosines. So this tells us this guy is going to be equal to sine squared x plus cosine squared x, that was 1 here, and then minus cotangent squared x. Alright, now let's look at another example using our even and odd identities. So here we're given that tangent of minus 4.41, and we want to figure out how to write this expression as a trig function of a positive number. Now notice we saw earlier that tangent is going to be an odd function. So we can rewrite this as tangent of a positive number by taking the opposite sign of this guy here. Alright, let's do another example. In this case here, we want to write these two expressions in terms of sine and or cosine, and then simplify. So this first one's pretty simple. We have cosecant x times sine x. We want to write this in terms of sine and or cosine. Well, we know that cosecant x is just the reciprocal of sine x, and that is multiplying sine x. So only one step there to write it in terms of sine. This is going to be the same as sine x over sine x, which we know is just going to be equal to 1. So this tells us cosecant x times sine x is just equal to 1. Let's look at this example B here. This one is a little trickier, but we'll do the same thing here. We'll write our secant squared theta and our tangent squared theta in terms of sines and cosines. We know that secant squared theta is the reciprocal of cosine squared theta. And we know that tangent squared theta is the same as sine squared theta over cosine squared theta. That was one of our quotient identities. All right. If we have a fraction divided by another fraction, we know that we can just multiply by the reciprocal. Doing so, we see that these cosine squared thetas here will cancel out, and we're left with 1 over sine squared theta. Okay, so as long as we keep these identities in mind that we saw at the beginning of this video, doing examples like this are not too difficult. But let's do a little more complicated one here. We're told that this expression here simplifies to either a constant, a single function, or some power function. So with that information, what we want to do is use our fundamental identities to simplify this expression. So the first thing that I see is we have cotangent and tangent here. So I think we can rewrite this, since cotangent is the reciprocal of tangent, to get something simpler. So like I said, cotangent is the reciprocal of tangent. This gives us, we still have this cosine squared over the sine squared x, but cotangent x times tangent x will just give us 1. Now we're not done yet because we told that the expression simplifies to a constant, a single function, or a power function. So we're not going to stop until we get either one of those. Notice that we have cosine squared x over sine squared x. This is one of our quotient identities. Remember, cosine x over sine x is equal to cotangent. So we'll rewrite this as cotangent x plus 1. And then this would be cotangent squared x, because we have cosine squared over sine squared. Now, if you remember, this is actually one of our Pythagorean identities. 1 plus cotangent squared theta is going to be equal to cosecant squared theta. So this simplifies to cosecant squared x in this case. All right, and this will be our final answer, because we were able to simplify this to a single power function. All right, so the last thing we're going to look at in this video is verifying identities. So here is a 6-step process in order to do so. I'm not going to go over each of the steps here, but we'll use them in the next several examples. But essentially what we want to do is, for example, here, verify this identity. We want to show that this left-hand side of our equation does in fact equal the right-hand side of our equation. Now, the most important thing to do when we're verifying identities is to, I think it says it in this step here, we want to try to rewrite the more complicated side of the equation, and then make the more complicated side equal to the simpler side through simplification. So, for this example here, obviously the more complicated side is this one. So I'm just going to rewrite this. Just so it's clear what side we're working on when we're simplifying. So what we want to do is rewrite this in a simpler way. Well, the first thing that I'm going to try to do is maybe factor the numerator, and we can do that using a difference of squares. So if you remember from your previous math classes, difference of squares formula looks like this here. If we have a squared minus b squared, we can factor this into a plus b times a minus b. And in this case, what we have here is a is going to be equal to tangent squared x, and b is going to be equal to 1. And that tracks here. We have a squared, so that would be tangent to the fourth x minus b squared, which is just 1 squared. So with this, we can rewrite this guy in this form here. So this will give us tangent squared x plus 1 times tangent squared x minus 1. And this is all over our denominator, tangent squared x minus 1. Now notice we have tangent squared x minus 1 and tangent squared on the top and tangent squared x minus 1 on the bottom. So these guys will cancel. And we're just left with tangent squared x plus 1. Now what we want to do is keep in mind what we're trying to show. We're trying to show that this is equal to this. So what we'll do is we'll keep simplifying this until we end up with this on the left-hand side. And remember, this is actually another Pythagorean identity. Going back to the top here, 1 plus tangent squared theta is going to be equal to secant squared theta. So, completely simplifying this using that identity, we end up with secant squared theta. Now notice we have that the left-hand side of our equation is exactly equal to the right-hand side of our equation. So we have verified that this identity that we started with is in fact true. All right, let's look at another example. We want to do the same thing. We want to verify this identity, make sure that this is exactly equal to this here. And again, what we're going to want to do is try to simplify the more complicated side. We can see here that this guy on the left-hand side is a little bit more complicated than this guy. So I'm going to rewrite this, again, just so it's obvious what side we're simplifying. Okay, so we want to work with this right-hand side here. The first thing that we'll do is rewrite secant squared t using the Pythagorean identity we saw in the last example. So this is equal to 1 plus tangent squared t, and this will be over our denominator of tangent t. All right, the next thing we'll do is split these guys out. Remember, we always want to keep in mind the goal, what we're trying to find. We're trying to show that this is equal, or this is equal to this here. So splitting this up, we have 1 over tangent t plus tangent squared t over tangent t. Now notice, this right here is cotangent t, which is one part of what we're looking for. And then this term here, we have tangent squared t on top and tangent t on the bottom. So this will cancel and we'll be left with just tangent t here. And so what we found was that cotangent t plus tangent t is equal to this here. And we did so just by simplifying the more complicated side of our identity. So we've verified this identity. We've showed that this is equal to this here. Okay, so for the last example, we're going to look at a more complicated one here. We want to verify this identity. And at first, it might not be super obvious which side is more complicated. However, I would say this side is a little more complicated. We could work with this side and we would end up with the same thing, but let's work with the right-hand side here. Also, another useful tip for verifying these identities is to write everything in terms of sine and cosine and then simplify the results. A lot of these identities can be broken down to sines and cosines. So we'll do that in this example. We're going to work with the right-hand side and we're going to rewrite what's in the parentheses in terms of sines and cosines. So we know tangent theta is the same as sine theta over cosine theta. And we know that secant theta is the reciprocal of cosine theta. So that's what we have in our parentheses here. Now just combining these, we have the same denominator here. So this is the same as sine theta minus 1 over cosine theta. Now what we can do here, distribute this exponent to both terms in our numerator and denominator here. So we get that on the top, and on the bottom we just have cosine squared theta. Now what we'll do here is use our distributive property for this here. So expanding this, we have sine theta minus 1 times sine theta minus 1 all over cosine squared theta. And then like I said, distributing, so we'll distribute the sine theta to both terms here, and this minus 1 to both terms here. We'll end up with sine squared theta minus 2 sine theta plus 1, and then this is still all over cosine squared theta. All right. Now notice we have sines in our denominator but cosine in our numerator. It might be helpful to rewrite this in terms of just sines because that's what we're trying to get to. Our final answer will be in terms of just sines. So we'll use the Pythagorean identity here to rewrite cosine squared theta in terms of sine. Now if we subtract sine squared theta on both sides of this guy, we see that cosine squared theta will be equal to 1 minus sine squared theta. So we end up with this here, all over 1 minus sine squared theta. Okay, so now we have everything in terms of sines. And looking back, we want to get something of this form here. We currently have a 1 minus sine squared theta in the denominator, but we want to get a 1 plus sine squared theta. So let's see if we can maybe factor these guys into that form here. And just to make our lives a little bit easier, let's say sine theta is equal to x. If we do that, then this guy here in our numerator is a simple polynomial. It becomes x squared minus 2x plus 1. Now what we can do here is factor this. This is the same as 1 minus x times 1 minus x. Additionally, if we're letting sine theta be equal to x, then in the denominator we have 1 minus x squared. And this guy can be factored as 1 minus x times 1 plus x. So with that information, we will factor the numerator and denominator of this guy. We'll end up with 1 minus sine theta times 1 minus sine theta over 1 minus sine theta times 1 plus sine theta. Now we can easily see that these guys will cancel in the top and bottom here. And what we're left with is 1 minus sine theta on the top, and then 1 plus sine theta on the bottom. All right, now going back to our original identity, that is exactly what we were trying to find. So by simplifying this more complicated side of our identity, we showed that the left-hand side was in fact equal to the right-hand side, and so this identity is true.